Let's continue our discussion of part 4, superluminal effect. We are going to propose a new mechanism. This mechanism allows the wave to propagate in the middle section. So it's a propagating wave, not an evanescent wave. So this is the idea. Region 1 is the standard waveguide. Region 3 also the standard waveguide. And region 2 is an undersized waveguide. Remember, in a previous part, we changed the width A to increase the cutoff frequency or decrease the cutoff frequency. But now the width is the same. So cutoff frequency is the same in region 1, 2, 3, regions 1, 2, 3. But height change from B to H. So it's an undersized waveguide, but undersized in a waveguide height, and length is L. How to measure? First, we generate a signal, sinusoidal signal, and we use a pulse generator to modulate this pulse and obtain a wave packet like this one. Then the wave propagates to power divider, divided into two parts. Part 1 goes through reference to adapters. Part 2 goes to two adapters as well as device under test. Okay, so we have an extra length. This extra length just like L. And then we have equal lengths for these two. Let's compare, measure on the scope, and we can measure the difference. Red curve is the incident, and blue curve is the signal passing through the device under test. So we can measure the group delay easily. Okay, so here is the experimental result. We have multiple poles, and we can measure the group delay from the web packet. Okay, experimental result just like this one. And this is the group delay, and this is the frequency, but it's normalized the frequency. And experimental result is red dot. Okay, and a triangle, open triangle with solid line is time domain simulation. As we expected, that agrees quite well. For a length of 10 centimeter, the total delay should be 0.33 nanosecond, roughly about here. So below this dashed line is fast wave, faster than the speed of light. And above this line is slow wave, propagate very slow. So let's look at this case. Okay, here, let's slow wave, for example, here, that's slow wave. Incident signal, transmitted signal, delay. So wave takes a lot of time. But amplitude, transmitted amplitude is about the same, just like incident wave. And for the phase wave, for example, here, B here, C here, as you can see, almost no difference, no delay at all. Delay time close to 0. Yeah, very small, very small. But amplitude, of course, is much smaller. But at least almost no time difference. Okay, so it can be classified into phase wave as well as slow wave. How to analyze this effect? It can be decomposed into incident wave, reflected wave together with phase, transmitted wave together with phase, and another section, section 2, sections 2 to 3, incident wave, reflected wave, transmitted wave. So at the there is discontinuity here as well as discontinuity here. And this discontinuity will result in phase difference, time difference. Okay, this discontinuity is caused by higher order modes. They cannot propagate. They just evanescent waves, but they will modify the amplitude and the phase of the dominant mode. Okay, so here is the effect of waveguide high. This is the waveguide high, normalized waveguide high. Minimum value is 0 and maximum value is 1. And this is the group delay at group velocity. Since group velocity is faster than the speed of light, so we give it another name, apparent group delay. Looks like the group delay. Looks like group velocity. Okay, so at here, phase for undersized waveguide below this value, the group velocity faster than light is clear. And transmission, here is transmission. Open blue circle that correspond to transmission. Okay, so for a transmission of 47% happen to be 1. When we change the length L, since it's a uniform waveguide, so the transmission should be the same. Yeah, transmission the same, very high. And delay differ by the length, of course, makes sense. Okay, so the whole system makes sense. It's a propagating wave. So in summarize, a short summarize, we propose a new mechanism and analyze theoretically and do the experiment. And in contrast to the two traditional mechanisms, evanescent wave tunneling, and traditional mechanism involve evanescent wave. Our mechanism employ a propagating wave. This mechanism features high transmission, yeah, very high. We achieve 3% or 5%, and all the result just 0.1 or at most 1%. And it's very broad bandwidth. Okay, looks good. What else? Now we have the ability to manipulate the group delay. We can change the group delay. And we are going to propose two structures to change the group delay. One is change the boundary, change the shape of the boundary. So we will propose a boundary time due to the existence of the boundary. And then by changing the polarization, we can also change the group delay. So another two new mechanisms. Okay. So first one, in this time, section 1, section 2, section 3, 1, 2, 3, the same waveguide geometry. What the difference is, boundary 1 here, an iris, a small hole. Boundary 2, a small hole here. Okay, so other techniques are the same, separate into 3 regions, but for sure, it's propagating wave in the middle. Okay, so 3 regions, incident, inward incident from here reflected, we have extra phase, and we have transmitted signal together with phase. And another boundary, outward incidence, we have incident reflected extra phase, Okay, put them together and we obtain this result. Look, maybe just focus on part B. We have this structure and we can perform high frequency structure simulator. Okay, HFSS time domain call, but we can calculate the transmission. Okay, so solid red line is shown here, and multiple reflection theory we will mention quickly, and triangle, blue triangle as experimental result. You can see here they agree very, very well. When passing through this region, it takes about 36 picoseconds. And however, in this region, very broadband, it's about 0. And we know it's slow wave here. And here, this region is fast wave. What happened here? And what happened for slow wave? What happened for fast wave? Here, after analyze the transmission reflection, we can decompose the group delay into several parts. Okay, and I will define all the equation. So first one is dwell time. This is the effective time for the signal standing within the system, excluding boundary dispersive effect, dwell time, and the lifetime of studied wave energy escaping through the both ends of fabric pillow cavity, including the boundary dispersive time. And this is multiple reflection. And when we pass in through the two boundaries, we will result in two boundary transmission time. That's a new. People do not expect this time before. And boundary reflection time. And this one should be times the multiple reflection because the wave bounce and forth inside. So boundary reflection time also takes some time. And we have another terms, dispersive time, due to frequency-dependent reflectivity. But this is relatively small compared with these three. Okay, now we analyze almost everything. Okay, now the wave can be simply classified into slow wave and fast wave. What is their criteria? For slow wave, it's unresonance, it's constructive interference. The wave will bounce back and forth inside and stored in the cavity for a very long time, but transmission will be high. On the other hand, phase wave is of resonance, it's destructive interference. Do not store inside for a very long time, just a very short time. Therefore, the wave propagate looks like the group delay wave looks like propagate at very high speed. Okay, the next question is it possible that group delay becomes negative? Yeah. My answer is yes, it's possible. In a birefringent waveguide system, we change the polarization. Okay, a negative group delay in a birefringent waveguide system. This time, waveguide is also divided into three regions: region 1, region 2, region 3. Region 2 is slightly different. Waveguide middle size, a central waveguide radius is the same as this one, input output, but we have two extra lengths, 10 extra slot. This provides a mechanism to change the polarization. So we can adjust the polarization of the middle section. So wave can be trapped inside or we have the multiple polarization, two orthogonal polarization. Yeah, so we can control the group delay. I don't want to show you how we control the group delay. Let me just show you the result. Okay, this is the group delay we measured, and from the web packet, you can see here the black dash line is the reference signal, and output pulse profile is shown here. As you can see here, it's group delay in these regions, just like this one. It's negative, not positive. But also have other region is positive. So polarization provides a degree of freedom to control the group delay. Okay, here is the result. By changing the polarization, changing the angle, okay, we can achieve, we have demonstrated a negative group delay in an anisotropic waveguide system. And we can control the group delay by changing the angle of the two polarization. So it's very convenient, very convenient. Okay, finally, phase velocity, Vp, is defined as omega over k as we expected. Group velocity is also the omega decay. Group delay is tau g, is defined as the phi over the omega is related with group velocity. And when group velocity is faster than the speed of light, we call it another name, apparent group velocity. And so here, we call it another name, phase time, because it's related with phase. Probability velocity for quantum mechanics, V probability, Jx over modulus of precise squared. Energy velocity, VE, Poynting vector over energy density. Okay. Information velocity, the speed at which information is transmitted through a particular medium. Signal velocity, the speed at which a wave carries information, but difficult to define for these two. Finally, I would like to thank Dr. Xinyo Yao. He is the first author. He spent a lot of time. Professor Xinyo Yao now. Okay. Also, we would like to thank Professor Herb Winford from University of Michigan. As you can see here, the first author for this 5 paper is Professor Xinyo Yao. So I would like to thank him again. Thank you for your attention.